Okay, let us move on. We are going into chapter 4 today, which is more on direct proof. And proof by contrapositive. So we're not going to do any new proof techniques at the moment. We're just going to be applying what we know already in some different contexts. Some background. There's a very important theorem called the division algorithm. It is not in our syllabus. I believe it's chapter 11, and we're only going up to chapter 10. But if you do a course in abstract algebra, well, we have two courses in abstract algebra here. There's an undergraduate version, and then there's a graduate version. If you do the undergraduate version, you'll definitely talk about this and spend some time on it, maybe 1 or 2 lectures. If you take the graduate version, it will at least be mentioned. I don't know if they'll actually go through it. But it basically tells us about relationships between integers. So for example, it says, if A and B are integers, then there exists unique integers Q and R with R between 0 and B such that you can write A as QB plus R. So you can sort of think of R as the remainder when A is divided by B, or etc. Right? And so your R has to be less than B, because if it were greater than B, you could actually subtract the B and put it into this guy. Right? So I'm not going to do the proof for that, but we are going to be using this fact to do a lot of things with it. So I thought I'd just mention it. Consequence of the division algorithm. So if we're talking about things, I'll sort of bring this back to divisibility soon, but let's say regarding divisibility by any A, B, C, and be written as. Okay. So there's, using this as a consequence, we can sort of express, whenever we're thinking about divisibility by a certain integer, we can sort of express all other integers in several ways regarding that divisibility. For example, if you're thinking of divisibility by 2, we already know about this. There are only 2 options, right? You're either odd or even. You're either divisible by 2 or you're not, right? So it means that any integer A, you can write A is equal to either a multiple of 2 or A is equal to a multiple of 2 plus 1. It means that you can divide by 2, but the remainder will be 1, right? Right? But it can actually extend further, right? So if we're talking about division by 3, then there are actually 3 ways to write any integer. 3n, or it can be 3n plus 1, right? Meaning you divide by 3, but you have remainder 1. Or you can divide by 3, but you have remainder 2, right? There's no plus 3, because if you divide by 3 and have remainder 3, it means you could have divided by 3 one more time, right? And it will never be anything bigger than 3 for the same reason, right? If you're talking about divisible by 4, then your A can be, 3n, 4n. 4n. You have 4n plus 1, you can be 4n plus 2, or you can be 4n plus 3. And that's literally all possibilities, right? So whenever you're thinking in terms of divided by 4, there are 4 ways to write every single integer, right? It's either divisible by 4 completely, or the remainder can be 1 or 2 or 3. There are no other options when thinking of divisible by 4. So basically, this pattern sort of continues. And it sort of works if you have to brute force anything. So any integer k, then your a can be kn plus 1, all the way up to kn plus k minus 1. Right? That's a general rule of thumb, right? And we're going to be using that all the time. It's a consequence of the division algorithm that we can write into this way. And we will be using that. Anything else I'd like to tell you to use for now? And I believe the theorem, there's a generalized theorem, but the theorem that we're going to be using, they're both positive. That's the basic one. And uniqueness is actually pretty important, but again, we're not going to talk about this theorem in particular. It's chapter 11 and the proof everything. We just want to be able to use the consequences of this theorem. Okay, we're going to talk about divisibility and all sorts of things. So let's talk about divisibility. First, let's introduce some notation. We say A divides B and write A, there's a straight bar down and B, right? That was, I actually got on the quiz what this notation means. If, what do you think it means? A divides B means A divides into B and there is no remainder. That's sort of the expression, that's sort of the idea that we want to capture. Can you describe that as an equation? Yeah, well, yes, we do need A not equal to 0, of course, because we can't divide by 0. But I need an expression.
B equals AC. So maybe it's A equals.
You think A equals?
No, it's B equals.
Right, it's the other one, right? So you have B is equal to A times C. What does that mean? If I divide both sides by A for some integer C, right? If I divide both sides by A, notice that the result is C, which is an integer. Once you divide an integer by another and the result is an integer, it means that one divided into it without a remainder, right? So this notation sort of means exactly this by definition. But this expression, sometimes I want to write an equation all the time, you can write that. It just means A divides into B and there's no remainder, right? And so you can express it with this equation. Okay, so that's definition I want, well, some more things. In this case, B is called a multiple A, and A is called a divisor of B. If A does not divide B, we write A, that bar, we put a strike through it, right? So that's not, right? So basically A does not divide B sort of means that it has one of these forms. It has the form of a division algorithm, but your R is not 0. Right? So that's what A does not divide B means. Means there's a remainder when you divide A by B. Anything else I want to mention? No, let's just jump into some proofs now. I gave you that definition, just talked about divisibility, what it means to be one integer to be divisible by another. And now let's actually do some proofs on this. Proof. A, B, C are integers with A not equal to 0, B not equal to 0, then let me put let. It's better to write it that way. I don't want to confuse it with a double if statement. Let A, B, C be integers with this condition. Prove that if A divides B and B divides C, then A divides C. That's just a start off. Very elementary property. I think your textbook also proves that. I'll just mention some of the other things it proves, and then we move on to some things more interesting. But remember this fact. This is a very important fact. You're going to be using this all the time. Okay, how would you go about this?
Assume that A divides B and B divides C.
Want a direct proof? Okay. Assume A divides B and B divides C. Then
B is equal A N
AN,
and C equals B L, where
L.
B N and L is argument.
That's correct. Then what can you say? C is equal to? Right, C is equal to BL, which is equal to AN times L, which is equal to A times NL, which means that A divides C since NL is an integer. Not so bad. Such a property is called transitivity, by the way, but we'll deal with that more in depth in chapter 8, I think. So it's an elementary property. It's one of the first things that people prove when they introduce division by divisibility to you. Other properties to know, some things that they prove right away that your textbook does. I'll just mention them here without proof because the proof is in your text and you can look at them. So if A, B, C, D are integers, with A not equal to 0, B not equal to 0, then if A divides C and B divides D, then AB will divide CD. Right? That's something that, again, you can prove in a very similar way. Another property that you should probably know, if A, B, C, X, Y are integers, with A not equal to 0, then if A divides B and A divides C, then A will divide any linear combination of B and C. Again, another very important property. I'm not going to prove it because your textbook actually proves it, and it's actually it's pretty easy to follow. I think if you read it, you'll get it. Let's prove this one though. Let A be an integer. Prove that if 3 divides 2 times A, then 3 actually divides A. Ideas? Huh? Yeah?
You can do what cases, since it's divided by 3.
by cases? What cases do you want to do?
You could say 2a equals 3x plus 1.
So you're thinking of doing cases where 2a equals 3x, or 2a equals 3x plus 1, or 2a equals 3x plus 2.
Yeah.
Okay, where would you go from there? How would you prove that 3 divides 8?
But don't you have the that it's divides
Remainder where?
if it's by 3, do we know that we have something left over? We need to prove that.
You'd probably need to prove that. I mean, this is true, but is it helpful? Like, we want to be able to say that 3 divides A, right? Which means A is just a multiple of 3, right? A would be 3 times. We need to show that A equals 3K. How can you use this to show that A must be equal to 3K? Yeah. Okay, so contrapositive is what I do because look at the expressions. One is talking about 2A, one is talking about A, right? So first of all, 2A itself is even, which is sort of weird to deal with, divisible by 3. 3 is an odd number. So that is kind of sticky. Having that 2 there makes things complicated because you notice on this side, if you divide it by 3, you get a 2/3 and it's an integer, so it's confusing, blah, blah, blah. I'd probably start here, right? So I'd probably do the contrapositive. Positive. Assume. What would we assume if we're doing contrapositive? 3 does not divide A. Then, what does that mean if I say 3 does not divide A?
Then we have cases.
Then we have how many cases?
2.
We have 2 cases. What are the cases? It's either 3K plus 1, so you have a remainder of 1 when you divide by 3, or
2 plus 2.
equals 3K plus 2. You can have a remainder of 2 when divided by 3, right? So remember, any integer can be written in 3 forms, either 3K, or 3K plus 1, or 3K plus 2. The ones that can be written as 3K are the ones that are divisible by 3. We're assuming it's not divisible by 3, which means it can only be one of the other 2 cases, right? So, in case 1, we would then have 2A, right? Which would be 2 times 3K plus 1, which would be 3 times 2K plus 2, right? So 3 does not divide 2A, right? Because 3 into 2A has a remainder of 2, right? So 2A is of the form 3 times an integer plus 2, and so we get not P, which is what we wanted. In case 2, 2A would just be 2 times 3K plus 2, which this we can write as 3 times 2K plus 1 plus 1. So again, 3 does not divide 2A because it has a remainder of 1 when we divide by 3. And the claim holds by the contrapositive. Okay. So again, when deciding to prove direct proof or contrapositive, choose the easier guy. They're always easier to deal with, and it gives you a head start. So sort of the opposite of like tackling things like trig identities, you always want to start with the most complicated side. Here, you start with the easiest side. So, any questions on this? Let's do another example. Let x be an integer. Show that 2 divides x squared minus 5 implies that 4 will also divide x squared minus 5. Note that the statement is not true in general. Just because something is divisible by 2 does not mean it's divisible by 4. But we're saying this particular integer, if it's divisible by 2, it's also divisible by 4. Ideas? What kind of proof would you do first of all? Direct or contrapositive? Direct, right? Contrapositive would actually be too complicated. Direct, we know what it means to be divisible by 2. There's a single equation. If I did the contrapositive, I would have to assume that 4 does not divide this thing. And then I'd have 3 cases to deal with, right? Either it has a remainder 1 when divided by 4, or 2, or 3, right? So going this way, I'd have to worry about 3 equations. Doing it directly, I only have to worry about 1. So I would do a direct proof here. So assume 2 divides x squared minus 5, then what does that mean? X squared minus 5 is equal to 2k for some k. Okay, what do we do now?
Can you say something true about x?
Come again? So you say x squared is equal to 2k plus 5.
What if we use when saying that for a number to be divisible by 2, we need to have x squared minus 5 to be even, and if we use when, for example, x squared minus 5 is even if x is odd, and then if we write if we use x, if, for example, x will be equals to n plus 1, and we plug it into the formula, and if we will be able to take out 4. Wait.
I'm not. Okay, I didn't follow you. So, first point that you wanted to make was what?
To use then that x squared minus 5 is even, then x is odd.
Okay, yeah. Then
X, we can say that x is equal to n plus 1.
x is equal to
N plus 1.
2n plus 1.
Yeah,
Okay, because it's odd. Yeah.
We can't use k for the n. And then if we plug it out, but we still have
Yeah.
You just said it since 4 is divisible by 2. Anything that's divisible by 2 will be divisible by 4.
No, that's not true. 6 is divisible by 2. It's not divisible by 4. So we can't make that proof.
If you plug in into the formula, into the 2n plus 1 into the left part of the formula, and if you will be able to take out of 2,
Yeah, so
then
I like this direction. Let's run with it. Let's actually write this down because it seems like we're getting somewhere. Sort of see where it's going. So now, do we have to prove that level, or is that clear?
we proved that.
Did we actually prove that?
Yes, or this is the work we proved it.
That specific one?
Which is on the.
I mean, it's clear. Note, if x squared minus 5 equals 2k, then x must be odd. So technically, we can prove this as a lemma. It actually won't be that bad, right? Because I can move the 5 over here. I can write this in the form 2k plus 1, right? And then I have that x times x is an odd integer, which we know that the only way to get an odd integer is if you multiply two odd integers. So technically it's going to be a lemma, but we'll say this is obvious at this point, right? So the only way to get an even number is if you take an odd minus an odd. We did that before, which means x squared has to be odd, which we've proven that if x squared is odd, then x is odd, right? So let's assume this. So then x I can write as 2n plus 1 for some n, for some integer. Then we can say, if I take x squared minus 5, it's the same as saying 2n plus 1 squared minus 5. And this will be 4n squared plus 4n plus 1 minus 5. Or in other words, it's going to be 4 times n squared plus n minus 1.
And if we take out if we have 4r, that means it's divisible.
Yes. This means that 4 divides, because this is an integer, x squared minus 5, since n squared plus n minus 1 is an integer. There's no space for the box. We have to have the box. We have to. Okay, how about another example? Let n be an integer. Show that 3 divides 2n squared plus 1 if 3 does not divide n. The only bit of hand waving in this group we did was this part, so I'll be like a textbook writer and said, reader should verify. So if you're not convinced of that, prove it. It's actually not that bad. And we proved that thing where I proved x squared is even if and only if x is even, you can use that to prove it. And let's look at this one. How would you tackle this problem? It's biconditional. I know how to spell the word if. That was intentional. We have to prove two directions, right? So, which direction would you prefer? This way? Let's do it this way first, all right? So, now it's probably a good time as any to introduce this. Sometimes when I'm lazy, I'll write something like NTS, right? Which basically means we need to show. A lot of people use that shorthand, so in the future, that's what NTS means. We need to show that 3 does not divide n, imply that 3 divides 2n squared plus 1. So now, assume, what would you assume? Right, so we'll do the direct proof because doing that is better than doing this. So we'll say, assume 3 does not divide n, then we have 2 cases. One, n equals 3k plus 1. Or the second possibility is that n is equal to 3k plus 2. In case 1, what do we have? What would we write? Huh?
2n squared plus 1.
Okay, start out with 2n squared plus 1, and we're hoping that we can write that as a multiple of 3. So in the first case, I'm assuming n is 3k plus 1, so this is 2 times 3k plus 1 squared plus 1, which is going to be 2 times 9k squared plus 6k plus 1. All right? And so what are we going to, so this would be 3 times
No, it should be 4k.
it should be
4. Because 2 times 6 is 12. 12 divided by 4.
where's 4k?
Instead of 6.
So we have, this will be 18, which is 3 times 6. This will be 12, which is, yes, that would be 4. 4k plus
1.
plus 1. Right? Because you multiply this out, you get 2 plus 1 makes it 3, which means you can factor out 3. And this means that 3 divides 2n squared plus 1. Right? Because we can write it as a multiple of 3. Since 6k squared plus 4. That's going to leave a mark. 6k squared plus 4k plus 1 is an integer. Now we deal with the second case. Case 2. In this case, we have 2n squared plus 1 would be equal to 2 times 3k plus 2 squared plus 1. We're at 2n squared plus 1. Okay, so this would be 2 times 9k squared plus 12k plus 4 plus 1. So this will be basically 3. I can factor out a 3. This will be 18, so that's 6k squared. I can factor out a 3 from this, and that would be what, 8? This will be 2 times 4, which is 8 plus 1, which is a 9, which I can factor out a 3 from a 9 to get a 3. And that's one direction. The other direction is this way. How do you do the second direction? So here we need to show that 3 divides 2n squared plus 1 implies 3 does not divide n. And in this case, we use the contrapositive, right? Because this is complicated, that side is easy. I'd start on this side, which means I'd have to use the contrapositive. So by contrapositive, assume, what would we assume? 3 divides n, right? We assume not that. Then, if I take, then that means that n is equal to 3k for some integer k, which would mean that 2n squared plus 1 would be equal to 2 times 3k squared plus 1, which would be 3 times 6k squared plus 1, which means 3 does not divide 2n squared plus 1. Okay. Any questions? Concerns? Issues? Okay, so obviously divisibility is getting boring. You guys are all great at it. So let's talk about something else. Congruence. Congruence. We say A is congruent to B modulo n. There are other ways to write this. You could say A is congruent to B mod n. They usually don't say modulo. No one says modulo. Everyone says mod. Or, and this you'll get when we do, again, chapter 8. A is equivalent, right? But we're not going to really explore what the basis of this equivalency is until chapter 8 to be mod n. Right? So there are many ways that you can say it and write this notation. A equivalent to B mod n if n divides A minus B. What's another way to express this? Yeah?
You said n divides A.
No, this particular phrase here, what does this mean? N divides A minus B. Translate it to an equation.
A minus B is equal to A, K of some K.
Right? It means that A minus B is equal to NK for some K. Right? Which is exactly the same as saying A is equal to B plus NK. People hardly write this, but I guess if you're lazy, you can write it. We write A equivalent to B, and they put the little n here on the bottom of the equivalency sign. I don't see that often, but I've seen it before. Right, and this is called two integers being congruent mod n. We will continue to explore this idea when we get to chapter 8, but for now, let's prove some elementary properties given this definition. I forgot to mention n is greater than 2 when it's an integer. Greater than or equal to 2. All right, so let's see. Example. I'm not sure if your text proved this, but the text would prove things like this. Let's say n is an integer, n greater than or equal to 2. Then, if A is equivalent to B mod n, then Ka is equivalent to Kb mod n for any integer k. Meaning, in many cases, we can treat this guy just like an equal sign. We can multiply both sides of the equation by a number and it won't change it, right? Any integer, in fact, and it will not change the equation. Proof. Assume what? Assume P, you want a direct proof. So assume A is equivalent to B mod n. Then what can we do with that? Then A minus B is equal to n L, or ln an integer. Then
Then you can just
it's an equation. We can multiply k on both sides, sure. These are just integers after all, and so we can multiply both sides of this equation by any real number and it will work. In particular, let's say we multiply by an integer. What can you say now? Just distribute Ka minus Kb is equal to n times Kl. And since Kl is an integer, we have that n would divide Ka minus Kb, which means that Ka is equivalent to Kb mod n. Right? And so about this, I'm actually not sure if we will prove it, so I feel like it will. So n is an integer, n greater than or equal to 2, A and B are integers. So, someone have a question? Huh? Show that if A is equivalent to B mod n and C is equivalent to D mod n, then I can multiply them. A times C is equivalent to B times D mod n. Ideas. I would go directly. So let's assume that A is equivalent to B mod n and C is equivalent to D mod n. And this guy's then what can we say?
A minus B equals nk,
Minus B equals nk,
and C minus D
C minus D
equals
nl,
and K
or kl
are
integers. Alright, then what can I say?
So we want to get AC is equal to BE mod X, and A minus B is minus
A minus what?
Can we do the part A minus B times the part AC minus B and then put it in K minus
You want to multiply them?
No.
Can you solve for A and C?
Let's say this would mean A is equal to B plus nk and C is equal to D plus nl. Okay, and then what do you want to say?
Plug into AC.
Then you say AC would be equal to, you just multiply these two, yeah? So we have B plus nk times D plus nl. No, distribute, right? So this is BD plus NBL plus DNK plus N squared KL. Okay, and what can we say to that?
subtract the over.
You could, okay, so we have AC minus BD. You didn't have to do that, but okay. Equals what?
N, and then BN plus K plus.
Right, so you factor out that N. So Bn plus dk plus nkl. This means C is congruent to BD mod n, since this guy is an integer. So if two numbers are equivalent, you can multiply them and the answers will give you the same thing. We're sort of exploring the equivalence here. We'll talk more about this when we do functions and also equivalence relations in chapter 8. Your book probably proved both of those, I'm not sure. I don't think it proved this though. What about addition? So A is equivalent to B mod n, and C is equivalent to D mod n. Then I can add them. A plus C is equivalent to B plus D mod n. How do we start? Direct proof? Assume A is equivalent to B mod n, and C is equivalent to D mod n. Then I can say A is equal to B plus nk, and C is equal to D plus nl for L and K integers. Okay, then what can I say?
A plus C equals B plus D plus K plus N.
Add the equation, right? Call this equation 1, call it equation 2. Then 1 plus 2, just adding these two equations give us, adding the left sides, A plus C, adding the right side, B plus D, plus n times k plus l, which means that A plus C is equivalent to B plus D mod n, since k plus l is an integer. So right now the notation might be a little bit abstract to you, what congruent mod n means. So I figured I would jump the gun just a little bit and sort of explain to you in more concrete terms what this means, and maybe we can get a proof out of it. And we'll stop after that. So here's a claim. And my claim is the following. So A, B, n are integers n greater than or equal to 2. Then, here's sort of a concrete way to think of congruence. A is equivalent to B mod n. If and only, it means it's equivalent to saying that A and B have the same remainder when divided by n. That is my claim, and I'd like for us to prove it. It's probably not something that you might see right away, so I'll give you a hint. Some of you might know. Hint. Someone try to come up with an argument for that.
so remember what notation I use.
So the division algorithm, they actually label the variables very intuitively. R sort of stands for remainder, Q stands for quotient. Right? So if you divide B by A, the quotient will be Q and the remainder will be R. And so that might also give you a hint. Right, so congruent, in two integers being congruent really means they have the same divisor when you divide by the integer n. Yeah.
For the bonus on the quiz, we actually know that A would be B mod n is this. A and B have the same remainder when divided by n. Would that be correct? Even though it's not really what it means. It's just that holds true for that case.
Well, it'll sort of always be true. Yeah, I'd give you the point. It wasn't what I would be looking for. I'd more be looking for you to write down the equation. Yeah, so ideas on the proof for this. Any idea which side would be easier, which side would be harder? Let's do the easy direction first. Going this way is easier?
But then you
Louis is divided by
Right, let's choose a direction. Which direction are we going? This way? Right to left? Who thinks left to right is easier?
which side is that one?
Okay, who thinks right to left is easier? It's like I'm just gonna choose that way. It's like,
Aren't it easier to use the direct proof to show if they have the same remainder?
well, that's this way.
Yes.
Okay, so assume A and B have the same remainder. When divided by n. What does that mean? How can you express this fact?
Can we say n divides a equals r?
Come in.
Can we say n divides a equals r and n divides b equals r?
N divides b.
Yeah, because n divides a separately, right? N divided by n, divided by n.
No, n doesn't necessarily divide a and b. I'm assuming that there could be a remainder. I'm just saying they have the same remainder. When I divide a by n and I divide b by n, I get the same remainder. So what is that? What? Yeah, so let r be the remainder. Like what would I be able to write down here?
Then x divided by n will be equal, for example, q.
You should say A mod.
A divided by n couldn't be q, because q would be an integer,
A mod.
which means it's not, there's no
A
remainder.
mod n equals B mod and equals R.
equals nk plus r, and then b equals nl.
A equals nk plus r, and b equals what? And L plus R. That would be correct. This means, if I only had this, that means n divides into a and I get an integer. But the thing is, if there's an r left over, that gives me a remainder, right? So it divides this plus there's something left over, that r is the remainder. Saying that the r is the remainder when you're divided by n is saying this equation. Right?
Then you subtract b from a minus b will be.
So this I can call equation 1, that I can call equation 2, and I guess you want to subtract equation 1 from 2. Then if I take equation 1 minus equation 2, I would end up with a minus b is equal to, the r's would subtract each other, they would die. I would just have nk minus nl, which is a minus b is just n times k minus l. And what does that mean?
Equivalent to B mod n. Since k is 7.
Right. So yeah, that was the easier direction. And notice that we didn't really use the division algorithm for it, though technically we sort of use it in the background, but not specifically in the form that I stated. All right, so now what? So if we're going this way, would you do a direct proof or a proof by contrapositive?
If you go
We could do a assume A and B do not have this direction I actually did directly, but let's see where we get with the contrapositive. Same remainder when divided by n. That means I can write, assuming there is some remainder, A is equal to nk plus this guy, and B is equal to nl plus this guy, with R1 not equal to R2, right? And K and L integers. Then what can we say? Yeah, sort of do the same thing again, right? So treat this as equation 1, treat this as equation 2. And so then we say 1 minus 2 gives us A minus B is equal to n times K minus L plus R1 minus R2 and since R1 minus R2 is non-zero, we have A is not equivalent to B mod n. Wasn't that bad? I did it directly, I did the division algorithm. Basically what I did was I wrote B as nq plus r, and then in this equation I plugged it in. And then I plugged that into A minus B equals nk. And you can get it directly by doing that. And then you say, oh, the r is unique, and so they'll have the same r's. You can do it that way as well. Yeah, contrapositive was also good. So congruence, I know it's sort of abstract. It means this other equation, but there's actually a method to the madness. It's just thinking of things in terms of divisors and remainders. And we're actually going to go into a lot more detail with that in chapter 8, where we're even going to develop a new number system where some strange things will happen. But it's a very nice number system to use. We'll end there unless there are any questions. Yeah. Questions.
I feel like for proofs like this, why can't we say something about how the difference is divisible? So if I guess it's kind of assumed that they will have the same modulo remainder.
If the difference is divisible, then they have the same remainder. Well, that is sort of what we said. We did take a difference and maybe, yes.
Can we just say it's kind of M5?
You'd have to argue that though. I mean, this is exactly that argument sort of written down. Like, I just took their difference and showed that it's divisible.
But is there a way to not write all of these words by this proof?
You have to write some other words. You have to show that, assuming they have the same remainder, then when I take the difference, the remainder will die. And so I'll get that multiple. You'd have to say that somewhere. But with equation,
is there a way to prove it just by numbers?
no, not that I know of. You have to be more general than that.